Hi, a warm welcome to everyone. Today, I'm going to discuss the behavior of conductors in electrostatic field, electrical capacitance, principle of capacitance of parallel plate capacitors, series and parallel combination of capacitors, energy stored in capacitor, energy density. Like that, we can cover these following topics also. Let's see what is behavior of conductor in electrostatic field. Let's see. You can see the figure from the figure from this figure. So you can see the net electric field is zero, and where is ep you have the positives, that is the electric field in positive side. Let's see, here you have the zero. Now you can see from this figure, we can say that one, the net electric field intensity in the interior of the conductor is zero. Why? When a conductor is placed in an electrostatic field, the charges drift towards the positive plate, leaving the positive core behind. At, behind, at an equilibrium, the electric field due to the polarization becomes equal to the applied field, so the net electrostatic field inside the conductor is zero. So here what is that one? At equilibrium, the electric field due to the polarization become equal to the applied electric field. You can see, and this will be called as the applied electric field, and this is about the electric polarization. Here the electric polarization and applied electric field both will be equal, then the net electrostatic field inside a conductor is zero. Second point about the conductors in electric field, this is our topic now. What behavior of conductors in electrostatic field. In second point, electrostatic field, that means electric field just outside the charged conductor is perpendicular to the surface of the conductor. The electric field just outside the charged conductor is perpendicular to the surface of the conductor. Suppose the electric field acting at an angle other than 90 degrees, then there will be a component E cos theta. A component E cos theta acting along the tangent at the point to the surface, which will tend to accelerate the charge on the surface, leading to the surface current. But there is no surface current in electrostatics. That's the reason when theta is 90 degrees, that means cos 90 is 0. That means it will be 0. You can see here electric field just outside the charges conductor is perpendicular to the surface of the conductor. Suppose the electric field acting at an angle other than 90, there will be a component acting along the tangent that the point to the surface, which will tend to the accelerate the charge on the surface, leading to surface current. There is no surface current in electrostatic. Why? Because theta is 90 degrees, cos 90 is 0. Not possible. Third point, the net charge in the interior conductor is 0. Why? The charges are temporarily separated, so total charge of the system is 0. So charges are temporarily separating, so that's the reason the total charge in the system is 0. That's the reason phi equal to E dot ds. That means E is nothing but E dot ds field and surface. Phi is nothing but flux. Then it will be from the Gauss concept, it will be considered as Q by epsilon naught, where Q is the charge, epsilon naught permittivity in null space. Since E is 0 in the interior of the conductor, therefore Q is 0 and Q also will be 0. So that's the reason inside the conductor the net charge is 0. Fourth point, charge is always resides on the surface of conductor. The charge is present on the surface of the conductor. You can see the figure. The charge is present on the surface of the conductor. plus charge, plus charge, plus charge. These are all the charges which are present on the surface of the conductor. Electric potential is constant for the entire conductor. So in a conductor, the electric potential is constant. So that is the reason dV equal to minus E dot dr. dV equal to minus E dot dr. So electric potential is constant for the entire conductor. Coming to the sixth property, surface charge distribution may be different at different points. So different at different points. So now you can take this one here. Sigma equal to Q by S. Sigma equal to is what? Sigma equal to Q by S, where sigma is nothing but Q by S, that is surface charge distribution may different at different points. Q by S, you can see this figure. Sigma is minimum, sigma is maximum. Every conductor is an equipotential rather than just an equipotential surface. So you are taking that one equipotential surface. In this equipotential surface, the conductor surface is different. So here, after that, the next character is about the electrical capacitance. What is electrical capacitance? Let's see here. The measure of the ability of a conductor to store charges is known as capacitance or capacity. That means the charge is proportional to the potential. The charge is proportional to the potential. Then remove the proportionality, then we will get a constant, that means C Q equal to CV, where C equal to Q by V. If V is 1, C will be Q. So Q is proportional to V, the charge is proportional to potential. Then remove the proportionality symbol, then Q equal CV, then C equal to Q by V, and this is the principle, this is the mathematical expression of the capacity. Capacitance of a conductor defined as the charge required to rise potential through one unit. So capacitance of a conductor defined as the charge required to rise its potential through one unit. The units of the capacitance is what? SI units of the capacitance is farad. Symbol is symbol of the capacitance is what? Farad. So, capacitance is said to be 1 farad when 1 coulomb of charge rises the potential of conductor by 1 volt. Then what is Faraday definition? Farad definition. Capacitance is said to be 1 farad when 1 coulomb charge rises the potential of conductor by 1 volt. Since 1 coulomb is the big amount of charge, the capacitance will be usually in the range of millifarad, microfarad, nanofarad, picofarad. Capacitance of isolated spherical conductor. Let's you take a spherical conductor which is in isolated nature. So in this conductor, in this isolated spherical conductor, what is the capacitance? Let's see here. You can see the figure. This is about the isolated spherical sphere conductor. You have at O the charge is positive and it is certain distance, the R is. So let a charge Q be given to the sphere which is assumed to be concentrated at the center. A positive charge concentrated at the center of the spherical conductor. Potential at any point on this surface. So here on this particular surface, the potential on this particular surface, the potential is what? So that is the potential at any particular surface is V equal to Q by 4 pi epsilon naught R. V equal to Q by 4 pi epsilon naught. What is that one? The potential at this particular point is what? Q by 4 pi epsilon naught. Therefore, C equal is what? C equal to Q by V. Now, substitute the value of the C equal to Q by V. So, Q is as it is. What is V? Q by 4 pi epsilon naught R. Then Q will be cancelled, and finally what you will get? 4 pi epsilon naught R. What is that one? 4 pi epsilon naught R. Then what we can understand from this equation? Capacitance of a spherical conductor. capacitance of a spherical conductor is directly proportional to its radius. The above equation is true for conducting sphere and hollow sphere. The above equation is true valid for conducting spheres, hollow spheres. Third point, if the sphere is in a medium, then C equal to medium. You are going to talk about the medium. That means epsilon equal to epsilon naught into epsilon r. What is epsilon? Epsilon equal to epsilon naught into epsilon r. This is about the medium. If the sphere is in medium, then C equal to 4 pi epsilon naught epsilon r into r. Epsilon naught is permittivity in vacuum, permittivity, relativity. ER means epsilon r. Capacitance of the earth is how much? That is 711 microfarad mu f. The capacitance of the earth is what? 711 mu f. Let's see, next one is about the principle of the capacitance. So step one, you can see the figure. So you can see this figure. You can see point A, plate A, plate B. Plate A is a positive, plate B is a neutral. Now bring the plate B towards the plate A, then what will happen? You can see here. At step 1, plate A is positively charged, B is neutral. In step 2, you can consider when neutral plate B is brought near A, charges are induced on B. So when you are bringing the the B plate induced by the plate A charges. So so that the side near A is negative and the other side is positive. You can see here in step 2. A is positive, one side is a positive, one side is a negative. When the further side of the B is at 10, so B is at 10, the positive charge and the B get neutralized, B is left only with the negative. So here the positive charge from the A plate will goes to the B side, but the B is at 10. Then what is happening? When B is at 10, the positive charges are absorbed by the earthen character, then in the B plate we will left over the negative charges. Now the net potential of the system, now you can see here, that means I taken two different players, one is the A, one is the B. This is the positive and this is the neutral one. Now you brought this one to the A, towards the A. Now from the A, whatever positive charges are moved there, the positive charges are goes to the B, and one side positive charges are accommodator, another side negative charges are accommodator for this neutral body. Now these positive charges will be attracted by the this earthen, and the leftover charges in the B is what? Negative charges. Now in A is what? There positive charges, in B is what? Negative charges. Now A is a positive, B is a negative. Now total net charge capacitance is, and total net charge is how much? That is plus and minus, that means 0. So here when the only with now the net potential system decreases due to the sum of the positive potential A and negative potential B. So here that means it might be going to be decreasing. So here the to increase the potential to the same value as was in the step 2, additional amount of charge can be given to the plate A. This means the capacity storage. Here what is capacity? The capacity of storing charges on A increases, and this is called as a capacitor. To avoid the nil value, to avoid the zero value, we are giving maximum positive charges to the A, and that positive charges are stored by the plate A, and that will be called as the storage capacity of charges on plate A is called as the capacitors. Capacitance of parallel plate capacitor. So here parallel plate capacitor is an arrangement of two parallel conducting plates of equal area separated by air medium or any other insulating medium such as paper, mica, glass or ceramic. You can see the figure. In this figure there are two different plates we have, and those two different plates are separated by certain medium. It might be air, might be wood, might be glass. So you can see the plates are having equal surface area, that is A. Now, what is the potential between these two plates? The potential is V equal to ED. But you know very well from the gas, E equal to is what? E equal to sigma by epsilon naught. Sigma by epsilon naught. E equal to sigma by epsilon naught. D is as it is. Now, again from the gas law, sigma by epsilon is what? Sigma by epsilon is nothing but Q by A epsilon naught. Q by A epsilon. Sigma by epsilon is what? So here sigma by epsilon we can consider Q by, that means sigma equal to Q by A. Sigma equal to Q by A. Otherwise sigma equal is what? Sigma equal to Q by A. Then replace here. Then V equal to QD by A epsilon naught. But what is C? C equal to Q by V. Now replace these values here. Q is as it is. Now V is what? QD by A epsilon naught. QQ will be cancelled. Then finally what you will get? A epsilon naught D. A epsilon naught D. This is about the capacitance of parallel plate capacitor. C equal to A epsilon naught D. If the space between the plates is filled with the dielectric medium of relative permittivity ER, then you can consider C equal to medium. So here, that is medium is what? Just you take the epsilon, not epsilon r, that is so medium, permittivity of medium, then epsilon equal to epsilon naught epsilon r, that you can see here. C equal to A epsilon naught into epsilon r by D. So here what we can analyze from this equation, that means the capacitance is proportional to area. Is it right? It is proportional to area and inversely proportional to the distance, spacing. Now combination of the capacitors, you can see now you are taking the capacitors. I am taking three capacitors, C1, C2, C3, and these three capacitors we are arranged in the series manner. Then what is happening? Let's see here. Charge is same in each capacitor, so you can see here in each capacitor the charges remains same. So you are taking this capacitor. In this capacitor we have three capacitor. In these three capacitor the charges remain same, that means Q, Q, Q. Potential is distributed inverse proportion to the capacitance. The potential, as we know that one, C equal is what? C equal to Q by V. That means capacitance is inversely proportional to V. That means potential. So here, that means here the potential is, the overall potential in this capacitors is what? That is V equal to sum of these three, V1 plus V2 plus V3, V1 plus V2 plus V3. But you know very well what is V, from C equal to Q by V, then V equal to Q by C. Now you can take here. So what is that one? V equal to, so V equal to V1 plus V2 plus V3. But you know very well what is V. V equal to, from the capacitor formula, V equal to Q by C. Q by C1, Q by C2, Q by C3. You know Q is common. Then what you will get? 1 by C1. Sir, 1 by C equal to 1 by C1, 1 by C2, 1 by C3. So this is, you can see V equal to Q by C, then V1 equal to Q by C1, V2 equal to Q by C2, V3 equal to Q by C3, where Q is remain constant as we discussed in first point. So now substitute these values, Q by C, Q by C1, Q by C2, Q by C3, Q is a common. Then 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. The reciprocals of the effective capacitance is the sum of the reciprocals of the individual capacitance. Individual capacitance. What we can note? The effective capacitance in series combination is less than least of the individual capacitance. Least of the individual capacitance. So now parallel. That means what? You can simply analyze. This is, for example, this is 3, 4, 5. So if you do the series method, if you find total value of the capacitance in series, and that value is less than 3, less than 3. Now coming to the capacitors are combined in the parallel manner. Now you can see the figure. That means here you pause v positive positive negative negative negative. See, you can see here what is that is all the positive terminals are connected to one point, all the negative terminals are connected to one point, and this will be called as the parallel method. In series, positive is connected to negative, negative is connected to the positive, but here in parallel positives are one side, negatives are one side. Now from this figure what we can analyze here, the parallel, so here in parallel combination potential is same across the each capacitor. So here the v is same across all capacitors. So we have three capacitor, in three capacitor the value of v is remain same. Now the second point, that is charge is distributed over the proportion to the capacitance. So you know very well C equal is what? C equal to Q by V. That means if it is constant, C is proportional to Q. C is proportional means if you increasing charge, according to the increasing of charge, there is a C also will be increasing. So now you can say that one, the charge is distributed over these three capacitors. That means Q equal to Q1 plus Q2 plus Q3. You know very well what is Q. Q equal to CV. Then Q1 equal to C1V. Q2 equal to C2V. Q3 equal to C3V. Here you can see why V not V1, V2, V3. We already discussed here. V is nothing but remain constant. The potential is remain constant too. So that's why we are not taking V1, V2, V3. Simply we taken C1, C2, C3. Why? Because capacity is vary. So now you can see V is a common, then V will be cancelled. C equal to C1, C2, C3, C. Now you can see Q equal to Q1 plus Q2, Q3. Therefore, by Q1 equal to C1V, Q2 equal to C2V, Q3 equal to C3V, and Q equal to CV. Now substitute this value. Then after simplification, we will get C equal to C1 plus C2 plus C3. Now, what is the effective capacitance? Is the sum of the individual capacitance. So the total capacitance is equal to the sum of the individual capacitance. And what we can note here, the effective capacitance is parallel combination is larger than largest of the individual capacitance. Largest of the individual capacitance. Now you can take here, this is 2, 3, 4. Now after the total value of this capacitance in parallel is greater than to this 4 value. Then energy stored in a capacitor. The process of charging a capacitor is equivalent to transferring charges from one plate to the another plate of the conductor. You can see once again, you can see the figure. What is that one? The process of charging a capacitor is equivalent to transferring of charges from one plate to the other plate of the capacitor, from one plate to the other plate of the capacitors. So the process of charging a capacitor is equivalent to the transferring charges from one plate to the other of the capacitor. You can see here, this is about the positive charge and this is about the negative charge. Now charge is transfer from one plate to the other plate, and this is about the charging nature. The amount of charging starts, there is a potential difference between the plates. Of course, when the charging is happening, if there must be a potential difference, there must be existing a potential difference between two plates. If the two plates are same potential, then it's not allow for the charging, it's not allowed the charging process. The plates must be different potential, then only the process of charging will be happening. Therefore, to transfer the charges against a potential difference, some work is to be done. The work is stored as electrostatic energy. Therefore, to transfer charges against the potential difference, some work is to be done. This work is said to be potential energy. So you can see here, this work is stored as the work is stored as electrostatic potential energy in the capacitor. Now you can see here, if dq be the charge transfer against the potential difference, if dq is the charge transfer against the potential difference v, then the work done is what? The work done du du equal to dw, dw equal to v dq, dw equal is what? V dq, where v equal to, from capacitor formula, v equal to q by c into dq, q by c into dq. Now, the total work done to transfer charge q is, integrate this one from 0 to q, that will be q by c the into dq, which will be u equal to 1 by 2 q square in by c, which will be, you can substitute the q value. What is q value? Q value is cv, that means c square v square. Q is what? Q equal to cv. Q square equal to what? C square v square. Substitute cc will be cancelled, then 1 by 2 cv square. You know very well what is cv. Cv is nothing but q. Then again in the cv square, cv v q v. This is about the work done in a capacitor. Now the topic is about the energy density. So here the work done is the potential energy in the form of potential energy is what? 1 by 2 cv square, 1 by 2 cv square. But you know very well what is cv from previous slide. C equal to a epsilon d from parallel plate capacitors. C equal to a epsilon d, epsilon naught d. Then v equal is what? V equal to ed. Now replace here 1 by 2 as it is. C equal is what? A epsilon naught by d. What is V? V is nothing but ed. Here V square, that means ed square. What is that one? E square d square. Here this is about the V square. C equal is what? A epsilon naught by d. So now you can see here d will be cancelled, and finally a epsilon naught e square t, a epsilon naught e square d. Now u by ad equal, u by ad, area and distance, u by ad equal is what? 1 by 2 epsilon naught e square. Therefore u equal to 1 by 2, that means energy density, u bar equal to 1 by 2 epsilon naught e square. The SI units of energy density, joule per meter cube, joule per meter cube. Now energy density generalized as energy per unit volume of the field. Energy stored in series combination capacitors. As we know, capacitors 1 by C, 1 by C1, 1 by C2, 1 by C3 in the series manner. Therefore, the energy stored is what? 1 by 2 q square is remain as it is, then 1 by C1 plus 1 by C2 plus 1 by C3 up to so on. Now, therefore, and this value will be considered as u1, u2, u3. Therefore, u equal to u1 plus u2 plus up to so on. The total energy stored in the system is sum of the energy stored in the capacitors, not dual, more capacitors. Energy stored in parallel capacitors. You know very well in parallel combination C equals C1, C2, C3. Addition, summation. Now U equal is what? 1 by 2 CV square, where C equal is what? C equal, you substitute the C1, C2, C. Now U equal is what? U1, U2, U3. Now the total energy stored in the system is the sum of energy stored in the individual capacitors. Now loss of energy on sharing of charges between the capacitors in parallel. Consider two capacitors of capacitor C1, C2, charge Q1, Q2, and potential V1, V2. The total charge after sharing is equal to total charge before sharing. That means CV. That means C1 plus C2 of V equal to C1 V1 plus C2 V2. Therefore, V equal is what? C1 V1 plus C2 V2 by C1 plus C2. Now, total energy before sharing, U equal to 1 by 2 C1 V1 square plus 1 by 2 C2 V2 square. Now simplify this one, which is a common here. Now you take here the V1 equal to V2. That means 1 by 2 is a common. Then C1 plus C2 of V square. Now total energy is what? after further simplification, this is about the initial, this is about the initial value, and this is about the final. You can see initial value and final before sharing, after sharing. Now you can see 1 by 2 c1 plus c2 of v square, ui 1 by 2 c1 v1 square plus 1 by 2 c2 v2 square. After simplification, ui minus vy, sorry, ui minus uf equal to c1 c2 of v1 v2 all square by 2 of c1 plus c2. That means ui minus uf if is greater than 0, or ui is greater than uf. Therefore, there is some loss of energy when two charged capacitors are connected together. Then they connected together, some loss of energy. The loss of energy appears as heat, and while connecting the capacitors may be become hot. So now when you two capacitor you connect, there you might be get some heatness, and this heatness is indicating about the loss of energy. Next, polar molecules. What is polar molecule? A molecule in which a center of positive charge does not coincide with the center of the negative charge is called polar molecule. You can see polar molecule does not have symmetrical shape. Example HCl, H2O, and NH3. That means what? Here, center of the positive charge is not coincide with the negative charge, and this will be called as the polar. Example is the HCl, H2. Whereas non-polar, center of the positive charge is coincide with the negative charge, and that will be called as the polar molecule, non-polar molecule. Coincide means center of the positive charge must be coincide with the center of the negative charge. Then it should be non-polar molecule. The example is N2O2. Then dielectric. What is dielectric? Generally, non-conducting medium or insulator is called dielectric. Precisely, the non-conducting material which included charges are produced on other faces, on their faces, on the application of electric field are called See here, that is the insulating material or non-conducting material will be called as the dielectric. If you are placing dielectric in the presence of the dielectric material in the presence of the external field, then this dielectric material will be producing the charges, inducing charges. Polarization of dielectric. When a non-polar dielectric slab is subjected to an electric field, dipoles are induced due to separation of the effective positive and negative. So here, then whenever we placing a dielectric material in the presence of external electric field, this dielectric material inducing positive charge and negative charge, and that will be called as the polarization. So here the dielectric constant is what? Here the dielectric constant can be considered as K equal to E naught by E naught minus EP, where E naught is nothing but electric field. EP means electric polarization. So here that means K equal to E naught by E naught minus EP. So this is about the topic. Thank you.